Yeah, welcome to Bookit Academy. Today we are going to be looking at once again epsilon delta definition. And remember, the epsilon delta definition is just what we can use to show that the limit of a function does exist, or to test the validity of the limit of a function. So we are going to be looking at this example, and it says show that the limit of that quotient function is equal to 0. So how do we do that? In the part 1 of this video, we highlighted some of the steps that are necessary to show that the limit of a function exists. And one of that is to establish the problem, or to understand the problem. So before we do that, we are going to be bringing out the parameters of this particular question. So let us carry out the proof now. Proof. We have to prove that the limit of this function is equal to 0. So the first thing we have to do is to bring out our function. That our function f of x is equal to, I believe you know the function of this given expression. So we have that our function is given by x raised to the power of 4 minus x raised to the power of 2 minus x plus 1 all over x minus 1. So this is the function. Then the next thing we would need is the limit of this function. What is the limit of the function? Do you know the limit of the function? Yes, the limit of the function is 0. So we have that to be 0. And our c is the value at which our independent variable is approaching, which is given by minus 1. So we have that to be minus 1. So with this given, we have to understand the problem. The problem is that we want to show that the limit of this function as the independent variable approaches minus 1 is equal to 0. So we are going to be stating the definition, the epsilon delta definition. So we can go on to say that by definition, that given any value of epsilon greater than 0, there should be a value for delta such that the absolute value of f of x minus L is less than epsilon whenever the absolute value of x minus c is less than delta. So this is the definition. So with this definition now, we have the first condition, we have the second condition. Each of these conditions, they go side by side, and we need them along the way. So the next thing we have to do right now is to substitute what we have here into this condition. So we can go on by saying that we have here to be given by the absolute value of x raised to the power of 4 minus x raised to the power of 2 minus x plus 1 all over the function all over x minus 1 minus the limit of the function is given by 0. So we have this to be the limit of the function, which is 0, and this is less than delta. This is less than delta. So that is the first part of our substitution. Whenever we have that the absolute value of x minus c, x is a generic variable, so we keep it as x. That is going to give us x minus c. We have c to be given by minus 1. When we substitute that into this, we have that to be given by plus 1. And this is less than delta. So this is where we are now. So we have defined this. So the next thing that we want to do right now is to simplify the left-hand condition, which is given by this. So when we subtract 0 from this given expression, we have the expression. So this is going to give us the absolute value of x raised to the power of 4 minus x raised to the power of 2 minus x plus 1 all over x minus 1, and this is less than epsilon. So this is what we are having. So what do we have to do next? The next thing that we have to do right now is that we have to establish a relationship between epsilon and delta. To establish that relationship between epsilon and delta, we would need to simplify this given expression. So simplifying this now, we have to get the factorization of the numerator. So to factorize the numerator, we have that to be given by, open bracket x raised to the power of 2 minus 1, open bracket x minus 1 all over x minus 1. So we have that the numerator is factorized. When we multiply these two brackets together, we are going to get the expression that is on the numerator. That is what we have there now. Now remember that the factorization of these this polynomial expression which gave us this can be done using polynomial division, but we're not going to do that in this video. So thank you. So this is set to be less than epsilon. So with this now we can simplify that. This cancels out this. We have this to be given by the absolute value of x raised to the power of 2 minus 1, and this is less than epsilon. This is where we are now. Now take note that we have here to be given by minus 1. Since we are having here to be given by minus 1, which is actually 1, we can also express this result to be given by x squared minus 1 raised to the power of 2, because 1 raised to the power of 2 is also the same thing as 1. Now, applying the difference of 2 squared, we can also show that according to the difference of 2 squared, if we have a squared minus b squared, a squared minus b squared is the same thing as a plus b, open bracket, a minus b. So we can apply that to this now, so that this is going to be given by x plus 1, open bracket, x minus 1. So this is that. So with this now, we can show that x squared minus 1 square, which is 1, is the same thing as x plus 1 times x minus 1, and this is less than epsilon. So how do we simplify this now? What we want to do right now is that we are going to apply what is called the properties of an absolute value. That is to say that if we have, for example, the absolute value of a times b, it is the same thing as the absolute value of a times the absolute value of b. So applying that knowledge here, we have this to be given by the absolute value of x plus 1 times the absolute value of x minus 1, and this is less than epsilon. So this is where we are now. Now that we have gotten to this point now, the next thing we want to do right now is to establish a connection between what we have on the left hand side with what we have on the right hand side. That is, with this given expression and this given expression. You can see that the second condition tells us that the absolute value of x plus 1 is less than delta. And on the left side of this condition, which is what we are having here, we can find the presence of the absolute value of x plus 1. So what do? We are going to carry out that same substitution, mere substitution. That is, wherever you see x plus 1, replace it by your delta value here. So this is going to give us delta times the absolute value of x minus 1 is less than epsilon. This is it now. So at this introduction of our delta, we are going to make delta the subject of this inequality. So from this now, we have that delta, when we divide both sides by the absolute value of x minus 1, we have that delta is less than epsilon all over the absolute value of x minus 1. So this is what we are having now. So given this value, we have gotten delta. But this delta value, which is less than epsilon all over x minus 1, is not exactly correct. It is an incomplete proof. So what do? Why is it incomplete? It is because it is known that delta itself has to be a function of epsilon and not a function of epsilon and another variable. Here we see that delta is a function of epsilon and x. That is, delta is a function of epsilon and x. But we don't want this to be so. What do we have to do? We are going to carry out further manipulation of this denominator. So this is how this is being done. So please pay attention. So we have this to be given by but from this denominator, where we are having x and we want to get rid of x out of this given expression, we have that the absolute value of x minus 1, is the same thing as the absolute value of x. Please, this is our absolute value here. Minus 1, this minus 1, let us put this minus 1 here. The minus 1 is there. So what do? Do you agree that if I add plus 1 here, plus 1, and I subtract 1, there is really nothing done in this now, because plus 1 minus 1 is also going to give us 0. So it means that this expression here is the same thing as the expression that we are having here. So what do? Now, the reason why we are introducing this plus 1 is so that we can have a conformity with what we have on the right hand side, which is this now. So let us simplify this now. So minus 1 is going to give us minus 2. So simplifying that, we have that this is going to be equal to the absolute value of x plus 1 minus 2. And this is equal to the absolute value, this is less than or equal to the absolute value of x plus 1 plus the absolute value of minus 2. This is what we are having now. So we take note that the absolute value of any negative number is a positive number. So this implies that we have this to be the absolute value of x plus 1. The absolute value of minus 2 is going to give us plus 2. This is it now. Now, since we are having a x plus 1, the absolute value of x plus 1 here, and we know that the absolute value of x plus 1 is less than delta from here, we are also going to carry out that same simple substitution. So it implies that we are having this to be given by delta plus 2 when you replace this absolute value by delta. So what does it mean? It means that our absolute value of x minus 1 is equal to this. But what is the value of this delta? So what we can do is that we can choose a value by saying, let this value for delta be equal to any number that is greater than 0. So you can choose any number that is arbitrarily greater than 0. So we can say, let delta be equal to 1. And if delta is equal to 1, it implies that this should imply that the absolute value of x minus 1, which is less than or equal to delta, is given by 1 plus 2. And this is equal to 3. So now we have simplified this expression to a whole number. So we can now substitute into the result that we have. So this implies that the value for our delta is less than epsilon all over 3. This is a value for our delta. So now our delta value has now been completely determined in terms of the variable epsilon. So that is as simple as it is. So what we are going to do right now is to complete the proof by saying that hence for every value of epsilon greater than 0, there exists a value for delta which is equal to epsilon all over 3, which is also greater than 0, such that the absolute value of f of x minus L is less than our epsilon whenever 0 is less than the absolute value of x minus c, which is actually plus 1, and this is less than delta. So this concludes our proof, and that is how we can show that the limit of a function exists using the epsilon delta definition. So please, thank you for watching, and at the end of this video you are going to see an exercise that you should solve by yourself and test your ability under this particular topic. So thank you for watching, and God bless you. Please do well to subscribe to this channel and give us a thumbs up. Tada!